So today we're going to be looking at exponential and logistic growth, also known as population growth. So let's get into it. So the exponential growth model is when something grows without bounds and it grows exponentially. So it starts off slow, and as it approaches further and further, as it approaches infinity, the graph will start spiking. Slope will keep rising and being greater. So the model, the function, is y equals a, which is a constant, times e to the kx, where k is a constant and x is a time variable. So as shown in the graph, like I said before, population versus time graph, that's what it usually is used for. If there's no bounds for a population, like say they have infinite resources and everything has perfect conditions, it'll grow exponentially until it reaches infinity. And yeah. So the derivation for this, how we arrive at this graph, how we arrive at this model, is we first start with slope. So that's dy dx, the rate at which y changes with x. So that's the slope. How dy dx, how population growth is affected by time, equals ky, where k is a constant and y is the function. Now what we want to do here is group like terms together, so the dy and the y, which is in red, and the dx we want it on the other side, so that it won't affect the y's. And when you do that, you get 1 over y times dy, or dy over y, equals k dx. Now we integrate. So we get ln of y, that should be absolute value. Ln of the absolute value of y equals k times x, where the bounds are 0 to y and 0 to x respectively. Now here we want y in terms of x. So what we're going to do is use the ln, which is a base e, and set e to the kx equals y plus c equals y. So that c is a constant, and that's going to be any constant in the graph. It's just a random number. So it'd be y equals e to the kx plus c. Now over here, you're going to look at it. It'll make sense later, but look at it as if it was e to the kx times e to the c. That's because when we set e to the c to equal to a, we'll get the same function we had before, where y equals a times e to the kx. We can set e to the c to be a because e to the c is a constant. It's a number, so it won't change. So we're putting an arbitrary letter for it. Now this formula isn't used as often as the next one is, because this only works if there is an infinite supply of resources around, which there usually isn't. So the next model, the population growth model, or the logistic growth model, it's defined as dp over dt. That's how population changes according to time, equals p times k, where p is population variable and k is a growth constant, times the quantity of 1 minus p over m, where m is the max capacity, the max population there can be. As shown in the graph, m is what the graph approaches, and that's in respect to t, time. Don't worry about the x. The x should be p. So what the function models is how a population changes according to how much time passes. So it'll keep approaching that max capacity. Now what we do use with this, we don't use this model in particular, but we use this to get the model that we will use in problems and how to solve for a population. So here's the derivation for population in terms of time. We start with dp dt. It looks like a lot, but when you go through it slowly, it's easy to understand. So you start with the equation before, And same as before, same as the other model, the exponential, you want to group like terms so that you can perform integrals on them. So just going really quickly, you do this, you get dp over p times the quantity of 1 minus p over m equals k times dt. M can be taken out of the denominator, meaning multiplied through, and you get m over p times the quantity of p minus m dp equals k dt. Now you integrate this. When you integrate it, you want to use separation of variables to get two integrals, with one with a constant over p plus a constant over m minus p. And when you do this, as shown here, you do this by setting 1 over p times the quantity of m minus p equals a over p plus b over m minus p. Now the a and b are different numbers. That's the numbers that are going to go over. So if we imagine we're solving for a and b, right? So when we do finally separate this integral, you're going to have these two integrals, the integral of a over p, whatever a is, dp, plus the integral of b over m minus p, dp, whatever b is. So you solve this by multiplying out p times the quantity of m minus p to get a times m minus p plus b times p. And when you simplify that, you get am minus ap plus bp equals 1. So that 1 can also be looked at as 1 plus 0p. So now we know that b minus a equals 0 and am equals 1. Thus, we know that a equals 1 over m and b equals 1 over m to be consistent throughout. Now we just plug a and b back in to the integrals that we separate. So you get dp over mp plus integral of dp over m minus p equals kt over m plus c. So that kt over m plus c, that's the integral of k dt over m. That c is another constant since it's an indefinite integral. Now when you integrate, you get ln p minus ln of m minus p equals kt plus c. You can use the ln rules where since it's subtraction, you can do p over m minus p and set that equal to kt plus c. You multiply m out, and so you get p over m minus p equals e to the kt plus c, since we want to get population in terms of time. And with that, you just multiply the other side by m minus p, so you get p equals a being e to the c, kt times m minus p. And then you separate, you do some math functions to get p on one side, and there you get p equals m over a e to the negative kt plus 1. So this, if we can go back to the other slide, models this function. So as you can see, the slope rises its fastest halfway. You can think about it like a rumor. Okay, so at first only 1 or 2 people know, so it's spreading slowly. But as more people know and more people are spreading, about when half the people know and half the people don't, it's a 1-to-1 ratio. So the people who know it are telling as many people as who don't know it, as many people as they can. And because it's half and half, there's more of a chance to spread faster, which is modeled here. And as more and more people learn, less people know about it or don't know about it, which is why the rate at which people learn the rumor or hear the rumor slows down until everyone knows it, which is that m value. Now this equation can be used in many places, like modeling the population of zebras in a zoo, or modeling the population of a city, as we'll see in the next example. Okay, so here's our example for exponential. So the problem states, A population is modeled by a function p that satisfies the logistic differential equation. Okay, so based on that question, we already know that we'll have to use the logistic formula, which is dp over dt equals kp times 1 minus p over m, which is already given in the formula, so we could use that too. So it says dp over dt equals p over 5 times 1 minus p over 12. So in part A, it says if the initial population is 3, p of 0 is initial, what is the limit as time goes to infinity of the population of the function? And same with if the initial is 20. Okay, so it's all based on the first equation. So if we go along, if we look at part A, you can see that so if you compare the two equations, the one that we know and the one that's given, it gives us k and it gives us m. So m would be our max population. That's what we want, which is 12. So no matter the initial condition, as you can see here, no matter what the condition is, the population will always max at 12. So even if it's 20, it's above 12, but it will go down to 12 because there are not enough resources. It's a limiting factor. So the max population the ecosystem or wherever this is can hold is 12. Thus both answers are 12. Now let's go to part B. If the initial condition is 3, for what value of p is the population growing the fastest? Okay, so remember the graph, the logistic curve? Remember how we talked about how when it's rising the fastest, it's when it's halfway to its max population, or the max people that know the rumor? The same thing holds true for this. As stated here, the population growth is always fastest when half of the max population, when it's half. So it'll be at when the population is 6, that's when it'll be growing the fastest. Which, if you see the curve, that'll be that middle where the slope is the steepest. Part C brings in the exponential part. Before was logistic, now it'll be exponential. If a different population is modeled by the function y that satisfies the separable differential equation. So it gives us dy over dt equals y over 5 times 1 minus t over 12. So for this one, I'd say solving would be easiest. It's quick, you don't have to think, you just solve for y. So if we look at this in part C, right below part B, the writing, we first separate dy and dt, we group, and then we take the integral of both sides. And when you do some math, you solve through, you get y of t equals a e to the t over 5 minus t squared over 120. So that's not our final answer though, because we need to find a. But they gave us the initial condition. Y of 0 equals 3. So when t equals 0, y equals 3. So we solve for a, we get a times 1 equals 3. So a is 3. Our final is 3e to the t over 5 minus t squared over 120. Now the last question is interesting. It says, for this function, what is the limit as y of t, as t goes into infinity of y of t? So what it's asking is, where will this go at t equals infinity? What's the population going to be like? Now, if we do the limit, we get 0. So this population of, let's say it did start out with 3. So before, there was initially 3 people. What this tells us is that as time goes along, those 3 people will leave and there'll be no one left. There will be 0 people there. And we know this by looking at our equation. We see that it's t over 5 minus t squared over 120. So when we do a limit, we want to look at the degrees of t, because that's what's changing. And because it's t minus t squared, we know that t squared will rise faster than t will. So that will become e to the negative infinity. and e to the negative infinity goes to 0. So 3 times 0 is 0. Thus the limit as t approaches infinity of the function goes to 0. Okay, so thanks for watching.